Okay, thank you. Ladies and gentlemen, thanks for our honorary professor, Leo Joskowicz. He comes from the School of the Computer Science and Engineering at the Hebrew University of Jerusalem, Israel. He's the founder and the director of the Computer-Aided Surgery and the Medical Image Processing Lab, the CASMIP Lab. And Professor Joskowicz, he is a fellow of the IEEE, ASME, and the MICA societies. He is the past president of the MICA Society from 2019 to 2022. Next, let us welcome Professor Leo to deliver the opening speech for the conference. Thank you.
Okay, thank you very much. I'd like to welcome everybody to the second day of this very interesting conference. I see that the program has many very interesting talks and very interesting presentations on very various topics of medical image and computer-aided diagnosis. And so that people have the time to do the presentation, I just had a one-slide presentation, which has to do with the role of deep learning in medical imaging and computer-aided diagnosis. So if I can share the screen, it's just one slide. Okay, do you see my slide?
Yes, we can see, Leo.
Okay, great. So my very brief participation is the following. Deep learning is great and has done great things, but I'd like to bring an analogy to leave you some thoughts so that when you listen to a talk, also think about the other things. And what's the catch with deep learning? So think of the following. You have a race car. This is your program that you're developing, and you have a certain goal, and let's call that goal the promised land. And for example, this could be a detection of liver lesions, segmentation of tumors, and different things. So you set yourself this goal, and you have the race car, and of course the goal is to get there. And here comes deep learning 5-6 years ago that basically promises you to give you a great engine. So you have this huge engine, very powerful engine that you're going to put on top of your car, because the deep learning network does not work alone. It needs an infrastructure and a context. And then you start working on that, and you discover that unlike the car you had before, the model-based approach, you have you need the gas. The gas, you need a lot of gas. The gas is the annotated data. You need much more data than you needed before. So yes, you have this great car and you have this great engine, but you need a lot of annotated data. And that's why you need to have a lot of gasoline. And in fact, the problem now becomes generating this fuel for this very powerful engine. So the production of annotated data becomes something which is very important because the annotation in our field is very expensive. It requires experts and different levels of experts, from the very senior radiologists to the junior ones. So this is a process which requires a lot of thought. And then you discover that, in fact, this promised land that they told you about is not that precise. So in the end, you have, in fact, you have to understand that there is an observer variability, so that the segmentation of a tumor or a lung is, in fact, has uncertainty in it. That means that if you give it to different observers, they will delineate a certain contour, but this contour has some variation, and they're both correct, but this is the variation. So that's why I put it in a blurred image, because it's not that clear. We know that for certain structures, if you have, for example, a dice coefficient between To readers, you know that it could be 0.9, 0.95, but there are other structures where even the agreement between two experts is low. For example, a dice of 0.7. And the same thing goes for detection. If you're detecting small nodules on the lungs, you know that the observer variability in terms of the detection rate, the precision and recall is not 1 and 1, but it's going to be 0.8, 0.9, depending on the size of the nodule. So unless you understand what is the uncertainty and what is this promised land, you don't know whether you're doing overfitting or not. So the second topic is, of course, it's great to be able to do annotated data, but how many do you need? What quality, meaning is this produced by a network, by a graduate student, or by an expert? And most importantly, the distribution. And there are many out of distribution things, and you need to understand what does it mean to be in out of distribution. There's a lot of work to do here. And then, of course, the method and the cost of producing, because you're sampling a complex distribution that you don't know about. So you need examples and you need to produce it efficiently. And finally, you need a pipeline. It's great to put a deep network, but for example, in this case, this very powerful engine is going to break the car. The car is not made for this type of engine. So the race car means the pipeline. What normalizations, what things you have to do before you use the engine and minimize the number of type data. And then, of course, there is the very technical work on the deep network itself, different architectures, training, loss functions. So the message I want to leave you with is that in our field, you need to think about all 5 things together. It's not sufficient to do one part of the work, but it's important to be able to quantify the observer variability, to understand how much data you need, and to build a proper pipeline around it. Thank you very much. So is there any host around here?
Yes, thank you very much, Professor Leo.
Sure.
And Professor Zhang is, maybe the device has some problem. Thank you very much for your very excellent and interesting speech. Yeah, Professor Zhang, can you hear us?
The device is, on
Okay.
site. Sometimes we mute ourselves because we want to avoid the echoes. Okay, thanks, Professor Liu. I think this is an excellent speech. I hope that in the coming years you can also still, work with us and give the report to the recent advances of your research work that really benefit us. And from the on-site, there are some authors. They have reported your previous talk have helped them open a new gate, and they know how to make their future research better with your valuable excellent report. Thank you again, Professor Liu.
Thank you.
Okay.
Thank you.